What's chemistry all about? Let's start part 2. How does it all work? Now, what's inside of an atom? Now, this is where sketching literally needs to come in. What's inside of an atom? There are loads of things inside atoms. Technically, there could arguably infinite things inside an atom, if you're going to go to the infinite realities paradox. But however, in our understanding of reality, there are 3 fundamental things that are inside an atom. Number 1 is the nucleus. That nucleus is itself made up of different parts. You can split it up. And the nucleus is made up of 2 particles, protons and electrons. And protons and electrons, they move a lot. Like, if I turn this moving ball on, then it'll move a lot because of how it seems to work out. Now, neutrons have a neutral charge, protons have a positive charge, and the thing spinning around the nucleus, just imagine the red line here, or the whatever color line here that's moving, is the electron, and the power button is the nucleus. This is basically what an atom is. Also, it's not usually spheres though. They're more complicated than that, I will have to admit. And the thing is, each of these particles themselves are created with some different element inside, like quarks, and those quarks can arguably, if string theory itself is correct, well, made of more parts. I want this thing turned off finally. Now, each electron is itself just one by itself, but protons and neutrons are heavier than electrons, and they're created with quarks, like up quarks, or down quarks, or just sideways quarks, or superposition quarks, like all those kinds of things. And that's pretty much how it seems to work. And that's basically what's inside an atom. And now, next thing that we're going to talk about is the periodic table. Noble gas is stable, halogens and alkali. There we go. That is the periodic table of elements. Or we could just... Luckily, unless those masks are away, this is basically what the periodic table of elements. However, if you want a more general view, then I'm gonna give you the one the book provides us with. If I can find it. Here we go. This is the periodic table. Now, by the time of this recording, the 117th element has been discovered, and these 5 elements have been renamed. Oh yes, correction. 7 elements have been renamed. It's not anubilium, anonuntrium, unquadrillium, pentillium, unhexium, unseptium, unoctium. Nowadays, they call them livermorium, like tennessine and organism, livermorium, and yeah, ionium, flerovium, moscovium, livermorium, tennessine and organism. They call that those now. And adumbium is now copernicium. So yeah, there we go, 2012 USBORNE science book. Ha! And this is how it seems to work. These periods right here are in the same group because of how the reactivity. As you go down on the left side, it'll get more reactive. However, on the right side, if you go up, it's wetter, and the further up you go is more reactive. The further you go down, it's least reactive. And that's just the least of our worries too. Because of how science works, there's also some weird, there's also a very good pattern. Each of these only have 1 electron in their outer shell, which is bad because now all I have to do is lose 1 electron just to be stable. Now let me explain. Electrons are made of orbitals, and these shells need to be filled up. Like some are full, like helium, which is a noble gas, and the first shell of an atom can hold up to 2 electrons. It needs only 2 electrons to be full. The second shell needs 4 more electrons to be full. So in total, if you want an electron with 2 shells to be full, you need 6 electrons. Oh, wait, correction. The second shell can take 8. And that's pretty much how it seems to work. Sodium itself has 1 extra electron in its outer shell, and there are 2 ways for it to fill it. 1 is to combine with somewhere here, or 2, just lose that electron. And you can do both of them at the same time. All the sodium has to do is lose the electron and then be attracted to sodium. Let me explain. Sodium chloride is table salt, the kind we eat. Now, sodium, Na, has 1 extra electron in the outer shell, and chloride, which is a poisonous gas, only needs one more electron to be added to its outer shell so that it can be full. So sodium gives chlorine one of its electrons, and then the chlorine atom is now negatively charged and the sodium atom is now positively charged. And so they attract each other, and that's why sodium chloride works. It's a white substance of solid proportions. It has a very high melting temperature and a very high boiling temperature too. And that's pretty much how it works. That's an atom for dummies. Next, we're gonna have to talk about sticking together. Now, stuff sticks together because of ionic bonds, the kind like sodium chloride connect to each other, or through chemical bonds too. Chemical bonds are not just attracted together magnetically, which we explained in the physics series, but in fact, it's just about how things seems to work together, it's like chemical bonds themselves, like electrons share an electron. Instead of giving an electron to them, you share an electron instead. And with that, you combine it together with a bond. And that's either you create a compound or molecule. Molecules are just two or more of the same elements combined, two of the same atoms combined together to create chemical bonds. And a compound is two or more different atoms, two or more different types of atoms combined together chemically to create a compound. That's basically the whole difference. And nuclear reactions are pretty much the weirdest things ever. It's like imagine two of these balls. And there are two ways nuclear reactions can work. Number one is the way that we've been using the longest, where you shoot something at an atom. That's very unstable. It splits, letting out a bunch of electrons and neutrons too, and with those neutrons bombard other atoms of the same type, which are also unstable, and that creates a chemical reaction. That creates a nuclear reaction that lets us create, well, two things: one, atomic bombs, and two, atomic energy. Now, the plausible source has been for a long time uranium, but there's a good reactor called the thorium reactor, and there's a bunch of benefits on the thorium reactor, and that will probably just let people be happy. Number one, it is really efficient, and it probably works. Two, it's really, really hard to turn into nuclear weapons. Really, really hard to turn into nuclear weapons. And three, it makes less waste, but same amount of energy. And that's pretty much it. The second way nuclear reactions work is imagine two of these balls, and then they smash into each other so hard that they fuse into new atoms. Now, usually protons usually repel other protons because positives, there's opposites attract, and sames, well, they're like bye-bye. Well, instead here, it goes so fast that this force goes so fast that it goes against the electromagnetic force, one of the four fundamental field forces of the universe. Now, the four of them are electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. The thing is, the strong nuclear force overcomes the electromagnetism of the protons and electrons to create new atoms. And it's that lets us create energy. And right now, it's pretty useless because we need to put in more energy. Our input is greater than our output. But hey, if it works in the future, it will work. And no waste at all. The catch cost. And I hope to see you guys soon. And so until next time, Schnan out. Peace.